Hi, my name is Xingwei Wang. I'm from Department of Electrical and Computer Engineering from University of Massachusetts Lowell, United States. I'm very happy to be invited to this symposium. Thank you very much. Today my topic is validation of an ultrasound transducer's generation and receiving function on one single mode fiber. This is the outline of today's talk. First, I will give a brief introduction about our lab, and then I'll talk about why we are interested in this topic, how we design the generator and the receiver on the fiber, and how we validate their functions. Finally is the conclusion part. Again, my name is Xingwei Wang, and you can also call me Vivian. My research interest is optical fiber sensors for biomedical applications, as well as the sensors for structural health monitoring and also the harsh environments applications. Why we are interested in optical fibers? Because you all know that optical fiber are well known for their small size. So they are good for a lot of applications that have very limited space. And also optical fibers are, that they are immune to the electromagnetic interferences. And also they are well known for distributed sensing, which means that the whole fiber, even is kilometers long, they could have hundreds, thousands sensing elements for temperature, strain, or other parameter measurements. So that's why we are very interested in the design and development of different kinds of optical fiber sensors. From previous talk, I think we have learned a lot of interesting ideas about how to generate the ultrasound from the fiber and also how to receive the signal from the fiber. So today's topic, we are going to focus on how to combine these two functions, the generation and the receiving functions, on one fiber. At the end of this talk, we have not achieved to do both the generation and receiving at the same time. What we did here actually is just to do the generation and receiving in a separate time zone. So how we generate the ultrasound from optical fiber, maybe the previous presenter have talked about that. So basically is the energy from the laser will be absorbed by the photoacoustic generation material on the tip of fiber, and that material will absorb optical energy and convert that into a thermal energy, and then the material will be expanded. And because we use the pulse laser, so when the laser off, the material will be contracted. So expansion and contraction then generate a mechanical wave. So this is how we generate this acoustic signal from the optical energy. So what we did here, actually, we take advantage of the gold nano composite material as the photoacoustic material. The previous speakers may have introduced a lot of different materials to serve as this photoacoustic material. Here, we dip the gold nano composite material on the tip of the 125 single mode fiber, and the thickness of this gold nano composite material is about 30 micrometer. Figure 2 shows the experiment setup to verify the generation efficiency of this photoacoustic generator. So again, the light is launched from the nanosecond laser through the fiber and reach the fiber tip is the photoacoustic material, and this material will absorb the energy and generate acoustic signal. We use a hydrophone to detect this generated acoustic signal. The whole test is conducted in the water. So this figure shows the experiment results. The figure A, the figure on the left, shows the time domain of the signal from the generated acoustic signal. So you can see that the P2P amplitude of the ultrasound pressure was 170 kilopascal. And figure B is the FFT of the time domain signal. And so this frequency also shows that the center frequency was 5.8 megahertz, and the 6 dB bandwidth of the transducer was from this 3.5 to 9.1 megahertz. Now we want to continue to validate that the same structure can be used as the receiver, the ultrasound receiver. So figure 2 is the experiment setup. So now the transducer was placed on the right hand side of this in this figure. You can see that the fiber optic transducer was placed on the right side, and then the acoustic generator was used as a glass slide. So on the glass slide, we also coat the photoacoustic material on it. So the same nanosecond laser launched the light onto this glass slide, and the material absorbs the energy and then generates this acoustic signal. So we use the same structure we just described before as the receiver now. And the detection actually is use a tunable laser, right? The light through the circulator and reach to this receiver. And then the reflected signal will be launched back through this circulator and go to the photodetector and reach the DAQ. So here is the experiment results. Oh, by the way, so after we use the fiber optic transducer to receive the signal, we replace that with a hydrophone in the same location, and then we compare the results from the fiber optic transducer and the hydrophone. So figure A is the signal from the optical fiber transducer, and figure 2 is the signal from the hydrophone. And figure 2 is the comparison result. Calibration result shows that the transducer sensitivity was 2.81 millivolts per megapascal. So finally is the conclusion. So as you can see that the same structure can serve as the generator and also the receiver, but they are not working at the same time because actually their central frequency is different now. So next step may need to design and develop one transducer can work both as the generator and receiver at the same time. That will be our next step. So thanks for the sponsor, National Science Foundation, to support our work. Thank you very much for your attention. If any question, feel free to reach us. Thank you.